So we're on confidence intervals. Yes. For me, I can't speak for everybody, right? I can't speak for everybody. I wish everybody would listen to me, but it's just not that way. So confidence intervals, what's the big whoopee to do, right? Well, it'd be kind of nice to say that, oh, I got this result and I'm about 80% confident. Well, it doesn't sound so great, but, or I'm 99% confident, sounds better. But confidence interval is just that. You have your number, right? I don't know, your result is 12.6, right? Well, what's the range, right? So that you're 90% confident, right? Or 80% confident. And that's all we're really doing. Ashley, what do you think that confidence interval would look like? Like if this is 80% confident, what would it look like for 99% confident, right? So these are just numbers here. I'm not sure. This could be like a 10 and this could be like a 14 or something. But for 80%, what would that interval look like for 90 or 99%? For 80%, yeah. Yeah, and farther to the, yeah, it's just bigger intervals all, okay? So it's kind of a little more informative than just saying plus or minus 0.2, right? These confidence intervals are a little more informative, okay? So we're getting more into statistics, and since we're getting more into statistics, you know, there's some really good articles and stuff here, but I thought this was kind of neat trying to get ready for this. In general, since we're talking about degrees of freedom, what the heck, you know, well, statistics. In general, the degrees of freedom of an estimate is the number of independent scores that go into the estimate minus the number of parameters used as the intermediate steps in the estimation of the parameter itself. Right? What the heck was that? Okay. So I don't know if my explanation's any better. A degree of freedom is a mathematical restriction put in place when we calculate an estimate of one statistic from an estimate of the other, of another. Now, the reason why I say this is because what is the difference between this and that? Or the difference between this and that? What's the difference?
Population.
Sample versus population. Population is all possibilities? Yeah, everything. These are mu and sigma. Mu is the result. Mu is it. Mu is the answer. Well, we're just trying to get estimates, x bar, of mu, right? We're trying to estimate it. We're trying to estimate the spread of our results, right? What's the reproducibility of these results, right? Again, we're measuring the same thing over and over and over, right? So what's the spread of measuring something over and over and over? That's a little s. Okay, standard deviation. But the true for the population is sigma. We don't know these. That's population. Those are the true values. Here's our estimates. This is what we get. Okay? So for example, if you calculate standard deviation, you lose 1 degree of freedom because you used up a statistic to get standard deviation. What statistic, Daisy, did you use up to calculate standard deviation? What statistic did you use up? Anyone know? Average. Average. There's an equation to calculate standard deviation, the square root, right? Average is in there. And I don't think I expect you to know this, but that's the equation for standard deviation. Average is used to calculate it. Yes, you used up a statistic. You used up an estimate is a better word, I think. You're already assuming something. Now you already lost some degrees of freedom. What is this? How is this important to us? Because we need to keep track of degrees of freedom, the number of estimates, because we have to read these tables so that we can. A lot of work in statistics went into getting the tables. We're not worried about that. We just want to learn how to use them. And to use them, we need to keep track of these degrees of freedom. Okay. So our first topic here is confidence intervals. And we said that mu was the average for the population, our true answer. X bar is our average. Well, we can have a confidence interval. Let's see, what is this table for? Oh, a whole bunch of different percent confidence intervals, right? Here's all our percent confidences. 50, 90, right? 99.9. And the equation, I'm pretty sure I give you all these equations. I'm not sure why I have a box over that. Whoa. Delete. There. TS over the square root of n. So what is, if you're going to calculate a confidence interval, so what it's going to look like is your average plus or minus some number. And the bigger the percent confidence of, hey, my result is within, I'm going to get the right answer within this range, right? And the more confident you are, it's just like Ashley said, that confidence interval is going to get bigger and bigger and bigger. Well, so that plus or minus number's got to get bigger, 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 right? What's this stuff? TS over n. What's going to get bigger and bigger and bigger as you increase the confidence? I'm going to be 99.9% confident. That's going to be a big interval in comparison to 50% confident. What's changing? What's getting bigger? Can you see it? Can standard deviation change on you? Because you've got a set number of measurements. Your standard deviation is your standard deviation. You can't do much about it. That's your data. N is the number of samples, measurements, right? That you did again, 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 again. The number of times you did it. Well, you did it so many times. It doesn't change. The only thing that's going to get bigger and bigger and bigger is your little t number, which you get from the t table. Yeah. So if you wanted to look one up, and let's say you had, I don't know, 10 measurements. Let's say you had 10 measurements, right? And your average is, I don't know, 69. Just making stuff up. You can write your confidence interval, right? It'd be TS over the square root of n. So you'd have the square root of 10 on the bottom. They have to tell you what your standard deviation is. Maybe they'll have you calculate it. I bet you the homework didn't have you calculate it. They're going to give you a bunch of data, and you got to calculate the average and calculate the standard deviation. Okay? But there's an easy way. There's an easy way. You're right. Shelby is right. The S word is, I don't know if I should say that on public YouTube, right? It's going to be ugly, but your calculator makes it so easy. So we have to figure out how to do that in a calculator. Okay, and we'll show you when we get to that in our first homework question there. So you're right. But that T number is what you get from the table. So if I had 10 measurements, right, and I don't know, if I want 95% confident, they made this one blue because I guess it's the most common. That's the number you plug in for T. Okay. So it's kind of better than saying plus or minus 7 or plus or minus 8. Confidence intervals give it a little more meaning.
They're going to tell you the confidence level.
Oh, they have to tell you in the question. Otherwise, which number would you pick? Right, what percent confidence? Yeah. Okay. If they don't, you just have to specify it, I guess, because you have to pick a T. Okay. So that's confidence intervals. Kind of a little bit better than just reporting a plus or minus number, getting a standard deviation or something. Destiny, t-tests. T-tests are used to compare one of those three choices of two sets of data. What'd you say?
The standard deviation.
It's averages, right? Because I guess for me, yeah, you wouldn't. I just have to remember it from the reading. But think of it the most applicable way. What do you get in the lab? What are you interested in? You're interested in the average. I mean, what this result comparison to this result? Oh, they got an 89.7. Oh, we got a 60 whatever. Right? We're interested in comparing averages all the time. Okay, and there's three cases. So are these averages the same or different? Oh, they look different, but statistically, you have to have some statistical founding on this. They're different at the 98% confidence level, right? That's where we're after, is being able to say whether averages are the same or different, and we're going to use t-tests to get there. So the book discusses three cases for using t-tests. So whenever, and this is how it always works, whenever t-calc is bigger than t-table, then the difference is, what would you say, Monica? Significant. Yeah, if t-calc, whenever you're calculating something is bigger than what's in the table, it's, no, this isn't good, right? Things they're not the same, or it's an outlier, whatever the case may be, whatever the test is. But so t-calc is bigger than t-table, the difference is significant at the, well, it depends on the percent table that you're reading, right? Whatever the percent confidence is. So here's our first case. We said there were 3 cases for comparing averages. Here's the first case. I'm kind of hard-pressed to think of one for this. Maybe Jesus can think of one. There's something that's been done a lot, right? The same measurement that's done a lot. Everybody knows the real answer for it. What would be an example of that? Snickers bar? Maybe. Something that has to do with something that's been done for an really, because to get a population of results it's infinity, you're never going to get it. But if you've been doing something for years, right, and you say, man, this is always, I don't know, some compound in Snickers that I'm not sure what they would exactly, how they'd measure it. Maybe some measurement they're doing. There's some load of peanuts in this cup, right? This load of peanuts in this cup is always 78.2. We've been doing this for 69 years. Same cup. 69.2 works great. We know that's the answer. So if you're a newbie on the line doing stuff, you don't take that into account. You use a different number, right? That's a known result. I think for me, this known thing is something that people just are really, really confident in. We've been doing it for years. That's it. So, I have another one that's known. We don't have, he's not here. Before students do a particular research project with me in the summer that deals with soil, we sent off for a known standard, okay? And we spent $300 for just a little pile of dirt. But this little pile of dirt was analyzed by about 12 labs, and they all agree on the amount of mercury in that soil. So that result is known. So the student can't continue, can't even start until they get the known answer. So that's an example of a known too, I guess. Okay. Wish I would have thought of that one before I drug out Snickers. Anyway, so it's not very common, but it's there. What do these bars mean? Javier, what do these bars mean? Absolute value. Known minus the average divided by the standard deviation times the square root of the number of measurements, and you get t-calc. And just compare it to t-table, right? If it's bigger, right, averages are different. A second case, replicate measurements but done by 2 different people or groups. Kind of nice because they're making Snicker bars in Detroit and making Snicker bars in Japan. You know, it'd be interesting to see if they're actually replicate measurements. They might be using new machines, old machines, robots and people, right? Anyway, when the standard deviations are similar, we're going to use equations 4-8 and 4-9. Where are they? Oh, here they are. Here's 4-8 and 4-9. They're getting kind of big, right? It doesn't look so bad right here. Oh, here's t-calc. X bar 1 is probably what? The average from set 1 or the group 1, right? X bar 2, the average from group 2. Not a big deal. So yeah, it needs to be 2 different groups, and they're both measuring the same thing. So their averages should be the same, except these 2 different methods, right? So by 2 different people or groups. No, they're done by 2 different people or groups. Sorry, different people or groups. So you do it, Shelby, and I do this activity, and you get an average, I get an average, and then, did we get the same result? So maybe I've been doing this for 80 years, and she's a newbie. So it's a good thing to test whether, can she go on her own or not? Yeah, Jamie.
Are those 2 people measuring the same?
Yes, the exact same thing.
But like if you're measuring, like you said, Snickers, it's the same peanuts, like 2 different people measuring the same.
Well, it'd be their peanuts, Japanese peanuts and ours peanuts. So yeah, life could be more complicated. There could be some issue with you're not actually measuring the same thing. Maybe they're using some weird freaking peanut than we are. But the point is think of it more like this way. You do a titration, Jamie, and I do a titration. You do it your way, I do it my way. Shouldn't matter. We better get the same result, right? So you do it a bunch of times. You have your little N1. Jamie's number 1. So Jamie did it so many times. I'm number 2. I did it so many times. She calculates her average. I calculate mine. The ugly thing is this S pooled. Look at that. Here's S pooled. It looks better right here, though. Okay. But again, S1 squared probably means what? Jamie's standard deviation. She's number 1. I'm number 2, so S2 would be my standard deviation. Okay. Okay? Now remember, the whole thing is we're comparing T-calc to T-table. So all of this is to get T-calc. But you have to compare it to T-table. When you compare it to T-table, the degrees of freedom now are N plus 1, N1 plus N2 minus 2. Because before, we've really used up 2 estimates. 2 standard deviations were used. So when you look up the standard, I don't know, let's say she did it 5 times, I did it 7, and then you got to subtract 2, that's 10. So that would be our degrees of freedom that we would use in this table, right? And then you'd read over and get your T-table number. That makes sense so far? Okay. Oh, same thing for this one. We didn't do this one. What would be, if you did 7 measurements, let's jump back to the known one. If you did 7 measurements, you have to find a T-table number, right? To compare it to this guy. How many degrees of freedom would you use? Right? Can you deduce it? Here we used sucked up 2 averages, so we had to subtract 2 from our total number of measurements, right? So our degrees of freedom was N plus 1 plus N2 minus 2. Here it would be just subtract 1 from it. So subtract 1, that'd be 6. Degrees of freedom would be 6. You used up 1 statistic. Okay. You used 1 estimate. Sounds better. You used up 1 estimate already. Okay. The average, so that was case 2, replicate measurements done by 2 different people. Average is obtained from 2 different methods. Ah, okay, so maybe Jamie does the titration, and I get to go play on the HPLC or some other fancy hoodoo-dicky way of figuring out the answer, right? So okay. So we use 2 different methods. Equations 410 and 411. This stuff is getting so big and long that I didn't even copy and paste it in here. Just have to look in the book. There may not be any homework on it. That's probably why I'm not worried about it. I bet you that's what it is, right? Okay, Q-test. Q-test. This you may, out of all this stuff, I think for this course, I can see you doing Q-test even in your very first lab here, right? This lab, a lot of labs we do are so individual. Everybody has a different unknown, and so you try to do your experiment 3 times. You should get the same result all 3 times, right? You kind of get the amount of calcium or something in there. One is kind of an outlier. Well, should I include them in the average or should I not include them in the average? I can't tell you. Albert can't tell you. You do the Q-test. Okay. So with the Q-test, when Q-calc is bigger than Q-table, then the questionable data should be removed, right? So whenever this Q-calc is bigger, it's something's messed up, okay? With blank percent confidence, right? I wonder how I can shut this off. There. Okay. I wonder if I'm supposed to be answering that. What if it's an emergency, right? Hello? Ah. It could be, right? Tornado. Here, and I just just made someone shut up. I think I better turn this back on. It's still ringing. Okay. With what percent confidence? In this case, it'd be 90. And there's Q tables that are different percent confidences. So in this case, it'd be 90% confidence. Okay. So I could see you using that one. Oh, gap and range. How do you get these? So to even use the Q test, what do you have to do with all your data measurements? Number them from smallest to biggest. I don't know. You're supposed to be getting 2 all the time. So you got a 2, 4, 1, and a 5.2, right? So let's make this one a 3. Let's make it more obvious of an outlier. There. Right? So the outlier definitely is that. Huh? The one's not in order, is it? Let's put the 1 over here. So your outlier is at 5.2. So the gap would be what minus what? 5.2 minus 2. And the range would be 5.2 minus 1. Exactly. How about the number of measurements? Count them all. Yep. Hello? I don't know what's going on. If it's that important, they should knock on the door, don't you think? Okay. So that looks good. F test. The book kind of did this kind of odd, I think. Let's answer the question first. You get an F calc. S1 squared over S2 squared. Nia, what's this S1 and S2 stuff again? What is it? Standard deviation of group 1 and standard deviation of group 2. Use the F, so when F calc is bigger than F table, the standard deviations are, it's always a bad thing, kind of. Different. And I'm not sure what the table says. I don't know, whatever confidence level the table's at there. Because notice how, I don't know if you caught this. Right here in case 2, when we're comparing averages, we're doing replicate measurements with the same, by 2 different groups of people. When standard deviations are similar or standard deviations are different, well, how the heck are you supposed to know whether they're the same or they're different? Right? Well, you're supposed to do the F test to do that. This is how you compare whether they're similar or different. You use the F test. So they kind of put that in an odd way. Okay. Let's see if we can jump right into this. So any questions on this stuff? So we've got plenty of time to work on these. So the percentage of an additive in gasoline was measured 6 times. So they're doing the same thing over and over, but only 6 times, with the following results. Okay. Find the 90 and 99% confidence interval for the percentage additive. Okay. So someone already said, oh, calculating that S is not going to be fun. Where'd it go? Okay. X bar plus or minus TS over the square root of N. Okay. So X bar is, now there's an easy way to do this. I know how to do it on my solar calculator. What I'm going to do, I don't care the numbers, I don't care the order, I'm going to plug them all in here. And I'm going to push a button, it's going to give me average. I'm going to push another button, it's going to give me standard deviation. You do that on a quiz or exam, I say good for you, right? If you go through the long way of doing it, I hope you have time, right? So, plus it's so much more efficient to do it on the calculator. So, if you're going to use Destiny's, let me hold yours up. Probably have to talk to Destiny because she's plugging in a lot of numbers. I think she knows how to do it. Right? You know how to do it? Oh, she doesn't? Does anybody know how to use average or standard deviation on this? Okay, Zach knows. I would ask Zach. If you have one of these calculators, I can show you right now. Okay? So, does anybody have this kind? Okay, there's several do. Okay, so in this kind, Oh yeah, yeah. I've got a bunch. Here, I have some right here. I've got a couple. Oh, that one you can't have. You just gotta sign your life away, Brad.
Got it.
Anybody else want one?
No, this one looks like a nice new one.
Okay. So on the solar ones, what you do is you get into standard deviation mode, and it kind of gives you a hint up there. It says mode.sd. So you have to push the mode button and dot and the decimal point. And little SD shows up in the corner. Okay, you got it so far? The little SD shows up in the corner. Now let's clear the statistics, because there might be something in there and who knows. So SAC clears all statistics, but it's yellow, so you have to push shift first. And I don't know why, whenever I'm clearing anything, I gotta do it a bunch of times. Once isn't enough. It doesn't, it's a psychological thing. So I cleared all the statistics. Now I'm ready to plug in all the data. There's my data. 0.13 is the first one. So I'm going to plug in 0.13, and I push the little data button, M+. And I do that for every single data measurement. 0.12, data. 0.16, data. M+ is data. 0.17, M+, 0.2, M+, and 0.11, M+. Okay, now all the data is in there. Now I have to find X bar on here. It's yellow and it's above number 7. So it's yellow and it's above number 7. So push shift and the 7 button. There's my average, 0.148. Okay, and the standard deviation is what little symbol on there. It's orange. It's a little sigma with a little n-1, because that's it. Sigma n-1. Shift sigma n-1. 0.034. It's right above the number 9. Okay. Now Zach's gonna be kind enough to tell everyone how to use. Right? How do you use yours?
I don't have one, but now how? If I
Okay, well, borrow Andrew's and tell everybody how to use yours. It's not that complicated, right?
No, you just go under stat, calc, and then enter your
So long. Go under stat. Go under.
All right, hold on. Yeah, there you go. List.
So go under stat, list. Okay, well, we'll let them figure it out. Well, now you can plug everything in. You know what the X bar is? Plug in your T, your S, and your square root of N. Well, get it into standard deviation mode first. So push mode dot. Right? And that little SD should appear. And then clear all the statistics. Clear all the statistics.
Got it. So we push stat first.
Yeah, you go under stat, and then just press 1 or enter to get to edit. And then you'll have L1, L2, or L3, depending on how many statistics you have. This is just one variable, so you enter all the data there. Whereas second quit, go under stat, calc, one variable statistics, or whatever sort of regression you want to do. So, stat, edit, enter your data.
Okay. Well, that's something that you can figure out at home too, right? But I would learn how to use those calculators. So in the end, you should get your result. Hopefully you get the same, you should get the same average and standard deviation as me. I do, because I don't know. Yeah, I mean, you could push, find the average, see if there's any numbers in there, but just, I clear it. Okay. what t number am I going to, at the 90%, I need to find my t. And at the 99%. So what numbers am I going to be plugging in there? You got to use that table. So which t numbers for the 90%? Is there a bigger table? There's a bigger table. Okay. I have how many measurements? 6? Why did I put square root of 10? Oh, there is 6. Okay. There's 6 measurements. So how many degrees of freedom am I going to be using? 5. Because you just used standard deviation, right? Standard deviation uses the estimate average. So you used up 1. So you have to look at 5.
So anytime you have a list of measurements, you subtract 1 and that's.
Well, it depends on what you're doing. If you're just doing an average, there's just an average. You're not using, you're just calculating an estimate. You're not using an estimate to get an estimate. But in standard deviation, you're using an estimate to get an estimate. I don't know if that makes sense. Because in that equation for standard deviation is average. And that's just an estimate. You're just guessing. So you just lost a degree of freedom. So when you're using that t-table, put it this way, I guess, Jamie. When you're using that t-table, never is your number of measurements going to be the same as degrees of freedom. I don't think. Because you're always, I can't think of an instance where you're not using average in the estimate. Yeah. Okay. So let's 90% confidence interval, 5 degrees of freedom. What's my t number? 2.015. That's my t. Right? 2.015. Do the same thing for 99%. You better have a bigger number for your t, otherwise you're doing something wrong. Ah, my S is, man, that phone. I bet you it's that phone, Daisy. How come no one else noticed that? I have to plug in my S. I plugged in my average twice. All right? You have to plug in S. T times S times the square over the square root of n. And notice it's not the square root of n minus 1. It's the square root of n. So plug in n. I have to look up the t value. You still have to look up the t value for the 99%. Calculate all this stuff. So in my answer, what did they do? I got 0.02. Okay. When you calculated this part for the 90%, did you get 0.02796 or something? Okay. Look at the equation. The equation is the square root of n. So you better plug in what n is. What's wrong with writing my plus or minus this way? I'm supposed to use how many digits? First digit. So this should read plus or minus 0.03, or 2 with a little, well, I'd say it's an 8 because look at that 9. Right? So there's 2 ways to write this. You should not write it that way. You should write it as plus or minus 0.03 or plus or minus 0.02 with a little dinky 8. Okay? So I need to have this agree. And I can't write 0.148. I have to write 0.15. Or I could write 0.14 with a little dinky 8. Yes?
I added, but you also subtract some 0.148 you leave it as plus or minus.
Plus or minus. So if you want to know what the actual interval was, add 0.03 to 0.15 and subtract 0.03 from 0.15. Because I have, my uncertainty here has to agree with my measurement because it's absolute. Right? So 0.03, this is the best way to report your answer. This is,
Why did you change that 0.148?
that's not my answer. This isn't my final answer. I just calculated the average. I wrote everything down. I didn't know what my uncertainty was at that time. I'm not reporting it. I'm reporting what when I'm drawing a box around. Yeah, you have to report your average to agree with your uncertainty. Right? Well, what place is this guy going to? He's going to the 100th place. I have to report my measurement to the 100th place.
But any other measurements that you used over here went to the thousandth place?
When you report your answer, that's the final thing that you do. You don't worry about reporting stuff over here in the calculation. In fact, you better carry all your digits over here. That's really important. You carry all your digits when you're doing this stuff. It's when you report your final answer. That's when you got to make the 2 agree. Okay? So you don't do any rounding or worrying about digits until the very final answer. And they have to agree to the same decimal place or ones place. Right, wherever it's agreeing. They have to agree. Yes? Take this times that, divide by the square root of 6. Right? How about the 99%? What did you get for your t number? 4.032? Anybody else get 4.032 for the t number? Yeah? Okay. So take that times 0.034. Divide it by the square root of 6. All right? And let's write my answer in red here. So this is not my final answer. I'm just writing out everything because I don't know where to report my answer. So I got plus or minus, what'd you get? 0.05596. I'm just writing a bunch. This is not my final answer. I'm just writing everything out. Okay. I can only report it to what place here? That first number, that hundredths. So I should write it as 0.06. That is a final answer. This is 0.06. That means I have to report it over here to what place? To the hundredths again. It'll be 0.15 again. That is my final answer at the 99%. Okay? Yeah, you didn't understand why what?
I don't understand why you round stuff.
Because remember going way back, we had to make numbers agree. Like 12 grams plus or minus what grams?
Yeah, no.
It has to be at the ones place because those numbers have to agree. Yeah. Yeah. You report it as you can report those many. They don't matter. They don't matter. This needs to agree with your absolute measurement, the absolute uncertainty.
Uncertainty, like, why did you go to the hundreds place instead of the thousands place?
Because that's too many digits. What's the convention? What was the convention? Go back to that last class. The convention is always to report how many digits? One digit. The convention is one digit. Unless it was percent, because no one likes to say 20%, they like to say 22 or something. So percent error had 2 digits. But the other type of error was only 1 digit. That's why. So if this is 1 digit, you round it to 1 digit. It just so happens it's at the thousandths place or the hundredths place. So that means this measurement has to be at the hundredths place. So there's a couple other ones here you can practice on. This one is where you compare 2 averages of people. And then I always have more here than we can talk about, so don't feel pressured. Okay. But come by and we can work some of this out. We'll probably do these too on our review during our review.